Hello, here we'll use nonlinear analysis to model large deformation of the coil spring. This model is made from solid elements. You can see them here, 20 node hex elements. So let's clear that and start from scratch. First we'll define the shape of the parametric curve generator. It's a helix, so let's have an angle P going from 0 to omega 6 pi, which is 3 revolutions. And give it a radius of 0.1 meters. In the axial direction, we can define the length as 0.1 meters, and multiply that by p over 6 pi. These three equations are the parametric equations of a helix. Let's have 60 elements and make them curved line 3 elements. Here it is. We also need the profile of that square section. The square comes out at 1 meter wide by default, so we resize it to be 1 millimeter. And then translate it to be positioned at the end of the helix, which is 0.1 meters away. We also need a guide path to control any twisting of that profile as it's revolved into the helix. We make another curve, same as the previous one, but with a slightly larger radius, an extra millimeter. There's our guide path. Make sure all the elements are joined together properly, open cracks. It shows that profile and the paths are not connected. So we need to join those with merge. We'll merge all nodes that are within 0.1 millimeters of each other. Use open cracks again, and you can see now they are connected. Let's also change this square from 4-noded quadrilateral to 8-noded. And now we're ready to use the sweep tool to generate the solids. That's the profile. Select that, accept it. To select the path faces, we'll use the circular selection tool. Select circle selection and drag from the center of the circle to include just the inside helix. Oops. Trigger that. Now we need to select the outside helix, so we can hold down the control key to get all the other faces that are not selected yet, including that one which we don't want. Oops. This is the guide path, the outside helix. Hit OK to generate the solids. Now we'll set up the analysis, make it nonlinear static. The load is going to be ramped up over several load steps. Let's have 10 steps. We'll give them a time of 1. This time of 1 second is just used to define the loads. It's not really time, just 10 steps. We'll fix one end, this end. Fix 4. And put a force on the other end. As I said before, this force will be ramped up, so we have 0 at time 0, and at At 10 seconds, the 10th load step, a maximum of 0.2 newtons. You can see on the graph that this force is now linear, goes up to 0.2 newtons maximum. Now we'll define a material. Just use some kind of steel, 200 gigapascals. And it's ready to solve. This will take a minute. On the graph, the blue line shows the error in the work on each iteration. Whenever the blue line crosses the dotted line, it means it's converged for that time step. So here at time step 4, it's just converged, moved on to step 5, the load is changed. It keeps doing that for 10 steps. If you push the cancel button before it's finished, it will retain all the time steps that have been completed. Here we are. So I'll have a look at the stress. 200 and something megapascals, that's quite high. Don't want to go much over that, or it will be yielding. Show the deformed view with an amplification factor of 1 so it looks realistic. And as you drag the slider, the load is increasing and so the deformation is increasing too. Clearly this is quite a large deformation. It's a highly nonlinear problem. This is why we're using the nonlinear analysis. That's all.